Hey there, and welcome. So today, we're going to dive into something really cool, kind of like a secret language that all waves speak. It's the hidden timing that runs everything from our power grid to radio signals. We're talking about phase difference. You've definitely heard someone say something is out of sync, right? Maybe it's the audio on a movie, or maybe two dancers who are just a little bit off from each other. But what does that really mean when we're talking about physics and engineering? Well, that's the mystery we're going to solve today.
Visit youtube.com/avidsystem and don't forget to subscribe.
Okay, so before we can understand a duet, we've got to get to know the solo performer first. To really get what happens when two waves meet, we need to start by looking at the basic rhythm of just a single wave. All right, so here it is, meet wave A. This is our solo act. You can see it has this perfectly steady, consistent rhythm. That's what we call its frequency. And it has a certain amount of energy, which you can literally see in its height. That's its amplitude. It's just a perfect, beautiful, repeating pattern. So a solo act is cool and all, but the real magic happens when a second performer joins in. Let's see what happens when they have absolutely perfect timing. So here's our original, wave A, just doing its thing, moving along to that same steady beat, but just hang on, because its partner is about to jump on stage. And bam, there it is, a second wave, wave B, just showed up, and it's moving in perfect lockstep with the first one. Just look at that. Their peaks, their valleys, every single point in between, they line up exactly. This is what a duet in perfect harmony looks like. Now, this perfect alignment, it's got an official name. We say the waves are in phase. And all that means is that they're hitting every single one of their marks, the highest point, the lowest point, and the exact moment they cross that center line at the exact same time. Their timing is absolutely identical. And this is the number you need to remember. When waves are perfectly in phase like this, the difference in their timing, what we call their phase difference, is exactly 0 degrees. 0 gap, 0 delay. They are perfectly aligned. Okay, but what happens when one of the performers messes up? What happens when their timing is no longer perfect and a little gap starts to open up between them? So check this out. On the left, you've got that perfect in-phase duet we just saw. But look at the right. Something's off. There's a really clear shift, right? They're still playing the same tune, the same rhythm. But one of them is starting just a little bit after the other. Now, they are out of phase. And this little timing offset, it's something we can measure with incredible precision. It's called the phase difference, and you'll often see it written with the Greek letter phi. It's just an angle, measured in degrees, that tells us exactly how far one wave is shifted from the other. And believe it or not, this one little number is the secret behind everything from those noise-canceling headphones you love to keeping our entire power grid from collapsing. No joke. All right, so they're out of sync. That brings up a new question, doesn't it? We need a way to talk about their relationship. You know, who's ahead and who's falling behind. I mean, if one performer starts before the other, we need some specific words to describe that. Who's setting the pace here and who's the one that's following along? Let's zoom in and watch really closely. See that? As they cross that center line, wave A gets there first. It's our leader. Then, just a moment later, wave B follows suit. It's the follower. Simple as that. And yeah, there's an official term for that. Our first performer, the leader, is called the leading waveform. It's the one that's just a little bit ahead in the cycle, hitting all its key points a fraction of a second before its partner does. And you guessed it, that makes our second performer the lagging waveform. It's literally lagging behind, always playing catch-up and hitting those same peaks and valleys just a moment after the leader. And for anyone who's curious, here's a little peek at how engineers write this down in their formulas. They use a plus sign inside the equation to show that a wave is leading or ahead, and they use a minus sign to show that it's lagging or behind. It's a really clean, simple code to describe this whole timing relationship. Okay, so you can probably imagine that drawing these squiggly lines all day would be, well, a total pain. So engineers came up with a much, much smarter and cleaner way to see this entire relationship in a single glance. I mean, for real, look at this thing. It's kind of messy, right? Trying to accurately sketch two out-of-phase waves just to analyze a circuit, it takes forever. And honestly, it's just asking for a headache. It's hard to see what's important here. But check this out. This is the brilliant solution. This clean, simple image is called a phasor diagram. And believe it or not, it tells us the exact same information as that messy graph we just saw. It's an elegant, powerful snapshot of the whole relationship. So how does this magic trick work? It's actually super clever. Each of those complicated waves gets replaced by a simple arrow, what we call a vector. The length of the arrow, that tells you the wave's amplitude, its strength. And the angle between the two arrows? Bam! That is the phase difference. By convention, the one that's further anti-clockwise is our leading wave. It's an amazingly powerful and simple visual cheat sheet. All right, let's do a quick recap of everything we've just covered. In phase means perfect timing, a 0-degree difference. Out of phase simply means there's a time shift between them. The wave that starts earlier is leading, and the one that follows behind is lagging. And finally, those cool phasors are the engineer's secret weapon to see this entire relationship in one simple snapshot. And that brings us to one last really cool thought. We've been talking about being out of sync like it's some kind of mistake. But what if it's done on purpose? What if that timing difference is actually useful? From creating noise-canceling headphones that use out-of-phase sound waves to cancel each other out, to aiming a radio signal in one specific direction, engineers are constantly and deliberately using phase difference to achieve some pretty incredible things. It's a really powerful idea, and something to chew on.
Thanks for watching.